and the front. But if it is lower priority, they can tend to just put this in the back, in the lower priority. So, but still, otherwise they will be keeping the first in first out property, keeping that way. And that's one things. Actually, why we put this together, the queue and the heap. Actually, they have a little bit the relationship. Actually, the implement such kind of data structure. Actually, we will be use different any. I mean, we can use array, we can use linked list, but best one is actually the heap data structure. And then that's the reason we need to put this in the heap. And then uh, of course the next question would be, what's the heap, right? Actually heap is the one complete tree based data structure. Of course, if you remember the the binary tree, they have a several type of tree. For example, complete tree, full tree. So that's the reason we need to understand what's the, we introduced before, but we are going to introduce again what's the complete tree. Then that's basically the based on heap of the data structure. Actually, heap is based on complete binary tree. They can able to represent the heap, then able to implement it. Then of course, priority queue will be used. The heap data structure get better implementation of the priority queue as well. And then finally, we will be going to introduce those are, and also there is a heap and BST is very time complexity very similar. That's the reason we are going to compare with that. And finally, we have also overview some C++ code or any other language code as well, if you in order to enhance the understanding. So at first, we're trying to understand the representation of the tree-based, of course, we always interested binary tree, but especially when we implemented heap, actually we interested complete tree. So first of all, what is a complete tree, right? So I'm going to just start from complete binary tree. I just give a several of several. There's a several article. I'm going to let you just quickly let you understand. So what's the complete binary tree? In the complete binary tree is actually the binary tree, but they have several properties. First of all, I mean they will be always they have a more, I mean, except the last level, except the last level of the height, I mean, except the last leaf level of the if level of the tree, other level always two child, and then and last level should be as possible to one child, and then that's one. Second is last level might have a, it is always trying to locate first the left side. I mean, it means can to look like a start first. I mean, there is not, doesn't exist that you just position first, I mean put first the right side element. Now I mean complete trees always start from the left to right. So that's kind of typical binary tree. So you can say that in second level always had two children, and then this is two children, but this one last one only one child. And that's a complete binary tree. But this one is not the complete binary tree. Why? Because the last trees should be, I mean, consider first left but not right. So that's not the complete binary tree. This one is a full binary tree. What's full binary tree? Always keep two. This is stupid. Right. And then complete And then this is actually the complete binary tree, because that there's children has a, and the second level is two children, but this one always try to start from the left side. That's a typical complete binary tree. This is also complete binary tree as well as full binary tree. What's a full binary tree is they has a always two children. You can say that this is two children or no children. Okay, I mean one is two children, two is two children, three is no children. So that's a sufficient property has in the full binary tree as complete binary tree. But complete binary tree is sometimes not full binary tree. For example, if this is one, this is two children, but this is not one. This if there's a two doesn't have children, then it's not. But so that should be enough to explanation complete binary tree, right? So next is how they can represent in the. Of course, this is whatever the complete tree, it's full tree, it's also binary tree. So they has only two children, or one child or no children. First of all, of course, the roots start from the one. Then we're trying to what I intend to do is I'm trying to represent the nonlinear data structure, which is that tree. I'm trying to convert with the linear data structure. That should be possible. For example, in the array way, or array data or linked list, whatever. In this here's I'm trying to start from the root, then put this in the, for example, the right. I mean, put this in the left and the right. I mean, that's keep that way. I mean, this is a 12 and 9, and then this is a 5 and 6, and then 10. So it means if this is a complete binary tree, then we can able to represent in the data structure in the both way, in the nonlinear data structure with the tree property and then linear. But it's not the you can say that it's not the sequential order, right? If it is about array, but it's fine for us, yeah. But it's not the complete binary. It's say that's complete binary tree, but the values doesn't seem like this. So that would be next question is, if this is a complete binary tree, how is be implemented in the different language? That should be they has a value, but they have a that's a typical definition of the tree. They have a value, but right and left side of the node, I mean, which is linked list, right? But it's a double linked list, right? Then now here is the create new binary tree. Of course, this is that's a grammar. Actually using the C grammar, that should be fine for compatible with the C. Then count of node, kind of recursively the calling this finally added, then you can find it. That should be fine. Check the complete or not, which is they going to check the number of index. So it is kind of understanding how, it's not our main idea of how to implement it, but actually they trying to understand what's the complete binary tree actually represent in the computer architecture. So that's one thing should be enough to how is the complete binary tree, right? The complete binary tree can be represented linear data structure way. And now I'm going, because complete, as I said, complete binary trees based on Heap is actually based on complete binary tree, implemented based on complete binary. That's the reason we try to explain first what's the complete binary tree first. Then if it is that we understand what's a tree, then we are going to understand what's a heap. Actually, the heap is actually, there is a two type of heap. One is a mean heap, another is a max heap. What is doing is actually the max heap means root always in the maximum value, put this in the root, and the mean heap is always minimum value, put it in the root. So it is kind of similar data structure, but different purpose. One is trying to get maximum, another trying to get a minimum. So actually heap, the abstract data structure, what that means is actually this is a kind of theory or definition, but they don't have a actually actually they can sometimes being called priority queue, or because they actually better implementation actually use the heap, so priority queue as well. So what does it means? As I said, there's a one they try mean heap, there is another's max heap. We also that's you can, if you're interested, you can read from, which is I told you. But there is a several things, there is a several operation they will be going to do it. For example, what's actually they will be created, what is actually they do operated, so how they can represent in the computer architecture. That's actually they give the very detailed implementation. More interesting that we just need to, for example, we just need to find the two things. As I said, there is a two type of, one is a mean heap, another the max heap. Assume that we're trying to focus on max heap, right? Means you need to find the maximum value in the list. So you find it. So its first step is extract the max value. But of course, you needed to first you need to create your heap. You needed to find max all the time, the minimum respectively, then insert add new heap. So which is operation is push, right? So you can put this, as well as you find the maximum, you can put this in the top. There is a, of course, if you delete the maximum, then you can find the next, what's the next next maximum, then try to move from the position to place where in the top, which is root. And if you creating, actually you need to create heap is the you create this node which is that has two pointer, I mean, which is that linked list, each node. Then you need to find position we are trying to create this, the structures, which is we can try to get this maximum. The process is being called heapify. Then actually the two process, I mean, there's left and the right. So they have been called this merge process. Then finally they will be put this together. So that's kind of basic process what they actually creating the heap, especially mean heap, especially max heap. And then how they implement it, as you can see, and then there is example that's max heap, right? As you can see, there is a 100, there is a 2 children, 19 and 36, and then the another, I mean, keep doing that different way to, you can extend the tree, but you also same time you can able to store in the linear data structure, so we can able to convert in between the non-linear to linear, which is, I mean, fundamentally we can able to represent in the computer. Otherwise, that should be doesn't exist such a way to you can implement it. So as you can, when you implement it, binary heap is, of course, you need to it's a, which is that actually using the binary tree, you need to find in the middle, then trying to split into two parts. You need to keep find this element. I mean, what's it trying to find? And the max heap is trying to find the maximum value. Min heap trying to find minimum value. So each time try to find the maximum value. As long as the find it maximum, they needed to go to the modes in the top. So that's the max heap. If you find, I mean, another case is min heap is find its minimum element. If you find it, the mode is in the top, which is root. So finally they will be recursively just find it most maximum or most minimum value, and then they will be represented in the top. So they can actually, after that, they can able to create the heap. So that's one thing. There is another article, actually more visual way to represent it, how the heap data structure being created. So for example, this is the heap data structure. First, if you try to use max heap, then that's max heap, that's min heap. I mean, this most of the, that's minimum. There is a maximum values in the top, in the root, and the minimum value in the root. So it's the two things, two different type of heap data structure. And then there is one operation being called heapify. That's important to understanding the algorithm, because as long as you destroyed the balance, what does means is if you doesn't exist, for example, you delete the let's say max heap, right? If you delete the maximum value, it means what's the next maximum value they have. So that's the process being called heapify. Heapify, the process creating heap data structure from the binary tree used to create maximum heap. Okay, that's being called max heap. So there's a create the complete binary tree first, because that's complete binary tree, right? For example, that's if this is array, to make it complete binary tree. So first element is root, then the second element is left. So this is right, this is left, and of the summary. This, so that's very easy to represent it, such a way. Then you need to, start from the index, last index, non-leap, where is n-1. Right. So for example, start from okay, current element I is the largest one, right? Then the index child is I to I plus 1, and give them child to I plus 2. Then left child, that's actually the algorithm itself. So that should be how they will be heapify process we will going to implement it. Now they trying to find, I mean, start from the last element, that would be, here's they trying to view maximum heap. They can see compared to 5 to 2. Actually, this 5 is bigger than 2, so that's when they're going to split it. Then of course they're going to compare in a higher position, so they will be put in the I mean, if there is compared to 3, I mean, there is a 2, 3, 4, 5. I mean, that's index, except this is level of the each index. Then they try to find heapify. The process will be guaranteed that keep doing that way. Then of course they finally they find the maximum value. When they trying to I mean, next question is how you can actually the coding level to implement it. Yes, so it means you need to, of course, there are two ways. One is a iteration process, another is a what's being called one is the iteration, another is recursive, right? So they both are saying that, yeah, as long as you, which one is you familiar with. That's the pseudocode to how they can Heapify process is going to implement it. So that's represent as left child. This is a right child of the algorithm. So you needed to start from the index. You needed to repeat it, the process. Then if the left child is bigger than the current large element, you needed to set left child index to the largest one. Also, to keep this way, they're trying to find the value. I mean, which is that swap is kind of exchange the position. Then they will be find what you need. For example, they're going to start from the first to end. They will start from the each of them. They compared each of the values, so that's Heapify process, actually linear complexity. There is a consider in this example how the insert element in the heap, right? For example, they trying to insert one element in the 7 here, but actually the element itself should be it's not the way, it's not the how to say, the last element, so that you can able to say that they will be going to Heapify with the file. I mean, they keep in the, if the situation your data structure is max heap, then you need to Heapify. Keep this the large value to move in the top. Actually, this is a, they will be in the second times they will already get in this right position. And then if you're trying to delete one more, for example, here's you're trying to delete 3, then what would be, what's the second situation? The algorithm actually, the algorithm when you delete it, they will be replaced in the last element. Last element is in the most right side element, in the left, which is the 5. They will be exchanged with the 5. Now they exchange with the 5 to 3, and then they will be then they're going to Heapify, but this one is after that they will be going to null it. After that null it means they can able to release it. So they will be, that's kind of the process, the Heapify, right? So this is heap structure. How the heap structure represent the linear way? Then of course they can able to using to computer based coding to represent, then we can able to apply it. So that's a heap data structure. We also talked about the max heap as well as min heap, right? So in this example, this is a representation of the min heap. This is a representation of max heap. Depending on the situation, you will be use min heap or max heap. Next question is how min heap or max heap will be represented for. Of course, we interested that those when they happen any situation, for example, delete or insert, they have a different time complexity. That's we interested to do. For example, insert a time complexity login, which is that very interesting, very efficient. Deletion also login time. That's very good. But the Heapify, when the first time creating Heapify, actually using the linear time complexity we have. And then this is a how they implement min heap and the max heap. actually the same, right? If you're able to implement it, one type of the heap, I mean max heap, you can able to implement min heap. But if you're interested to compare with that, there is a graph of comparison. I mean min heap k represent the root node must less than equal to among the k represent all those child. I mean that's a max heap is the max heap, the k represent at the root node must greater than equal to among the other k. I mean at least there should be greater each of the level of the element or equal. Second difference is min heap is the minimum k element that represent the root. Max heap is maximum element and they represent in the root. Min heap used ascending order. Max heap is descending order. Of course, the construction min heap in the smallest element in the priority has a priority, and the max heap is largest element has a higher priority. In the min heap, smallest element in the smallest element in the first to be popped from the heap, max heap, largest element first and pop in the heap. So that's a comparison. Yeah, min heap and the what? Max heap. I opened it 2 times, 3 times. That should be fine. Then there is another article, actually completely described from the at the beginning of the how heap data structure, actually the complete data complete tree. I mean here's the representation of the complete tree. Why is the complete tree? First of all, in the from the highest to last level of the h minus 1, it means before then the leaf of the level always have 2 children. Then after that they will be trying to position each element from left to right. So that's easier to understand how the complete tree been created. And then this is example of the what's the complete tree or not. I mean actually it's not the complete tree. This is not the complete tree, as well as it's not also not complete tree because this right side is then they already located in the right side, so it's not the way of the complete tree to represent it. This is also not as well as this is not the complete tree. If this one last one change the right to left last one, that should be complete tree. And then this is actually the example complete tree. As you can see, h minus 1 levels always two children they has or no children. Then last levels just start. I mean that's complete tree. That's full tree is also complete tree. That one is also legal. That one also legal. That one as well as this is also legal to complete tree, which is those are can be useful to represent the heap. So that's the fundamentals of heap. We can use it in the heap. And then max heap is trying to put this in the maximum element in the top. The process when they doing insert or delete it, they actually destroy the rule property. So that's the reason we needed to process the process being called heapify, right? And then this is they represent this is max heap. This is represent with min heap. I mean that's worse to you can see it. This that's very detailed article which worse to read. And then here's a several type of implementation with the array implementation with the I think several different type of implementation, right? But yeah, give them more details how they can implement it, right? With the, I mean that's the array, but this you can represent with the mean heap in the graphic way, so it's very visual to understand. There is a explanation of how the left side and the right side algorithm been implemented. That's kind of more important application, important method with max heapify, build max heap, find max, extract max, which is that, you know, when they delete or insert, they will be, you have to insert, you have to call it this function. I mean, in the mean heap also they have the similar functionality existed, because this is kind of full life cycle exists in the heap data structure. Whatever the mean heap should be mean heapify, build mean heap, find mean, extract mean, but reverse. I mean, max heap is just need to serve. I mean, 1, 2, 3, 4, 5, 6, 7. It is definitely necessary in the application. Application heap data structure. What kind of application will be used in the heap data structure? And a heap is efficient in the priority queues. One, it should be efficient to also use it. Then another is a graph data structure. We also used it in the heap data structure, which is that Dijkstra short sparse algorithm also used heap. So this is kind of two obvious algorithm, two obvious application used at heap, mean heap or max heap. Yeah, right. So if you're interested, you can read this article. So that's could be good. Next things that are probably right. Next things probably how we can implement it, right? Yeah. I forgot one thing, that heap sort as well. There's one of the sort algorithm, heap sort. Yeah, priority queue. Last one is we talked about one of the application implementers priority queue, right? So next thing is how the priority queue is implemented. Actually, there's a many. I mean, actually 4 types of implementation exist in the priority queue. You can use the array to implement it. You can use the linked list to implement it. You can use the heap to implement it, and then as well as you can use the binary search tree. You can use it as a data structure to implement the priority queue. The things that which one is better? Actually, the heap is the best one. So that's the reason we the title is actually heap and the priority queue. Next thing is that, you know, before that, I'm going to, I mean, just want to house the article implemented with the different, I mean, I think, all right. For example, first one is implement with the array. Of course, the priority queue, they should be has item as well as the priority, 2 things. And then you needed to input, you needed to output, you needed to retrieve. I mean, the terminology, of course, professionally, you will be NQ and DQ, right? So actually those things you need to implement it. So definition, let's see the C++ code of the implementation, definition of the data structures, each node, which is that value and the priority, and then all of the value you're trying to represent in the array way. I mean, they going to store, going to store 100,000. At the first, the size is -1. In queue operation is give them priority as well as value. So you needed to put this size. I mean, because the array, you know, we needed added in the last one. I mean, then of course, in the same time, you need to put the priority. Of course, peak is when you peak and the queues, they going to play with the priority. So for example, here's a peak is, for example, here's a mean heap, right? There's integer minimum at the first they minimize, initialize with integer minimum value is the highest priority. Then recursively trying to repeat it, the process, if the highest priorities of the each element, the priority as well as the ID is bigger than -1, I mean, should be, then, I mean, this is a IND is kind of index. Then as well as the value itself is bigger than that one, then priorities, then priorities will be changed, index also changed. If the highest priority, otherwise the highest priority, they will be replaced, also update the index. So then finally they will be returned the index. DQs output, right? When the output, of course, there is also linear recursive process from the index I to size of the array, then you recursively to trying to find. So as you can see, that the time complexity actually, I think, as you can see, time complexity is in queues fixed time, but DQ is linear time, because they will be going to, worst case, they're going to process all the value. If you're trying to use the priority queue is linked list, the time complexity is a little bit different. This is pushes, insert is linear time, but link array list, I mean, array is insert is fixed time, but instead of output is linear time. But if you use the linked list, output is fixed time, but insert is linear time. So interesting. So if you're trying to faster insert, then you need to use array. If you're trying to faster get, you better to use linked list. That's the conclusion of the time complexity, right? So that, I mean, you can pick and pop. You can get this very quick with linked list, but you cannot get quickly in the array. So interesting. But if you're interested, this is compared to linked list and array, right? But if you implement it with priority queue with the heap, the time complexity definitely extraordinarily different. As you can see, it's mostly, I mean, login time complexity, which is most better than, I mean, in average better than implemented with the array, but I don't think so. You know, depend on your what's the fixed time. If the fixed time is lower than login time, depend on how much the fixed time does means one time, right? If you remember, you say the fixed time is 1,000, but if your login time is, for example, million, and then login should be is 20, then yeah, then I would say heap is good. But if his element is 1,000, then this is fixed time is 10, and then would be the linked list and the array list should be probably have a chance to use it. So depend on what kind of value you can compare first them. Okay, so that's kind of yeah, heap. Prior to heap, you can use it. Heap should be, as long as the value is most large, then you can use heap. But otherwise, the shortest value, you can just use array, and the linked list is no problem, because the performance is better than heap if this short data set. Right. So I think this last comparison, you can use it, you know, usually efficient, unsorted, last highest priority usually implemented heap and the BST. But as you can see here, if you use the heap sort, best case is in login time. I mean, insertion sort is best case in time. Quadratic time is average. Selection sort is quadratic time is bad one, worst one. Small sort is also is not good at, but most, as you can see, heap sort is the most better one in login time. Yeah, so that should be wise. They will be recommended for. I mean, average sort, a merge sort also in login time. So it's kind of similar performance they have. Library, I mean, you can use it own implementation, but and the library in the C++, they have a standard library priority queue existed. You can use it. In the Java, they have their own class in the priority queue. .NET, they have Scala, Golang. Each language has own kind of priority queue implementation, because priority queue is such kind of one that using in the heap sort as well as some data algorithm. So yeah, right. So that's it. There's another article. The almost the BST's BST and the heap can be implemented priority queue, and both are similar performance. So depend on what kind of things. Some case, I mean, those two articles give you a some kind of hint to how when they can use it. I think which one? They have did a little bit kind of comparison. Depend on which one. I mean, that's interesting article you can read for. Definitely, if you get this such level, get this fundamental, then better to read this article as well. Okay, so I think that's end of the lesson. Let me just make a conclusion. So what we did learn today, we learned that actually one efficient data structure, how they've been created, then what's based on they created, which is that heap actually is abstract data structure, nonlinear abstract data structure, which is the tree, and it's binary tree, and then the complete binary tree is based on that created. And then also we, in order to understand maybe we mentioned it before, but we try to repeat again that what's the complete binary tree between the full binary tree. Actually, the properties efficient to represent a heap, and then the heap is itself. They have two types. One is a max heap, and is a min heap. Then max heap, min heap. Actually, the fundamental of the implementation of the priority queue. That's the reason we needed to put this together. And then when they using the max heap with the and the min heap, they actually have several operations. Is very interesting, which is that when they broken the balance, you have to heapify. What heapify is, let's say that max heap situation. They will be, when you delete or insert one of the element, they will actually they broke the balance. Then they going to forward. I mean, let's say upward to maximum value, extract from the last, then they put this in the top. That's a maximum heap. And the min heap is actually the reverse process. So there's another article, of course, they completely give them list of what's the max heap and min heap operation should be included. BISC implementation was insert, update, and heapify, extract heap, and create a heap, mean heap, and then such things, yeah, we have to learn. And then finally, if you understand, then as well as able to represent in the heap, present in the computer with the heap, then we beginning to introduce priority queue, because priority queue is the fundamentals of the best implementation of the heap. Of course, the priority can be implemented linked list, can be implemented with array and linked list, but if data source as bigger as then as bigger as the best performance heap will be retrieved, derived. So that's the reason heap is best one, because always we will be get better performance when they get this bigger data set. And the BST is also another choice, very close with the heap sort, heap data structure. So yeah, that's another choice. In the end, of course, there is a other little bit comparison of the comparison with the implemented heap to implement the heap sort. It's another example. In the future, we will be explain what's a heap sort, how it look like. But today, with the time, we just show that the one implementation with several implementations with priority queue. So yeah, priority queue, heap also is another application is, and graph as well can be used we will be introduced in the future. All right. So that's the lesson for today. It's time to question. Any question? So guys.